Thank you.
Okay. Can you hear me?
Yes.
Okay. Hello, everyone. And I will be talking about the overheating assessment method in Estonia, and a quick insight about the study we conducted here in Estonia. So first, the objects of the study were first to assess the overheating problem in existing apartment buildings. We conducted indoor temperature measurements for that in the year of 2014. Then to determine the compliance of these analyzed buildings according to Estonian regulations, and also to define a critical room that is most likely to counter overheating, parameters that define this room, and to get some solutions that are practiced that are good for overheating prevention. So the annex requires that overheating prevention is a priority, and it is also included in Estonian legislation. The requirement in degree hours. In case of residential buildings, we have a limit of 150 degree hours over a base room temperature of 27 degrees. And in case of non-residential buildings, we have 100 degree hours over the base temperature of 25 degrees. And this assessment is done during 4 periods of 1st of June till 31st of August during the summertime. And usually in non-residential buildings, we have mechanical cooling installed, or this means that there is no need for this specific assessment for these buildings. For this, to do or conduct the simulation-based procedure where some critical rooms need to be simulated and verified. A bit more this requirement of degree hours. Perhaps some of you do not know this, but I will just briefly explain it. So, for example, in this case, we have simulated this 3-month period indoor temperature in one room, and every hour that the temperature is over plus 27 degrees in case of residential buildings, this sum of degree hours, and it do not exceed this 150 and basically to calculate it, we have this every hour we have some temperature value. If it's 27 degrees, we get excess 0. If it's over, we get some excess, and we sum these, and if the sum is higher than 150, then the building is non-compliant. And in compared to non-residential buildings, there is a key difference in terms of ventilator cooling through window airing. So we can count this in residential buildings, and it needed to be simulated as well. So as I said, the compliance is proved by performing a simulation-based calculation for standard group types, and usually passive cooling solutions are preferred over active cooling systems, especially in residential buildings. And rooms that in which the internal heat gains are highest are basically needed to simulate. And residential buildings, this calculation is performed at least in one living room and one bedroom. So in one, at least 2 rooms need to be simulated. We analyzed 25 apartment buildings. We selected them randomly, and the requirement was set in place in 2009. So all buildings that acquired the building permit after that were selected or were chosen into the study. So these buildings need to have these calculations in order to get this building permit. And we conducted measurements in 22 dwellings and slated altogether 158 dwellings. About the studied buildings, most of these were massive precast or monolithic concrete structured buildings with usually more than 4 floors above ground. Also some transmittances for the building envelope shown, and a quite important value for the windows, the solar heat gain coefficient. This varied from 0.4 to 0.7. Now, for measurement, we used these temperature data loggers. We placed them into rooms away from solar radiation or other internal appliances that would affect the temperature measurement, and also some ventilation airflows. And the period was from 1st of June to 31st of August, and we recorded hourly average indoor temperatures. And of these measurements showed that of the dwellings we're expecting temperatures over plus 27 degrees for a remarkable portion of the measuring period, as can be seen here. And in some cases, the temperatures were as high as plus 32 degrees average. So, in some cases. And here the temperature excess for the measured buildings, and here you can see that if we could take the 150 line, then most of these would exceed this line. However, we have to acknowledge this is the measured year, and the year of simulations is quite different. So, and the height was 2,110 Kelvin hours, and it had a large unshaded windows and was west oriented, and also no cross ventilation in this case was available. So this was a quite overheated apartment. As already, the simulations were done for specific apartments. Rooms that were south or west facing with relatively large glazing areas, for example, and not all building, the whole building was simulated, but also these, so to say, critical rooms only, and also all shading, of neighboring building or tree was also moved. simulations needed to be with using Estonian test reference year climate. This represents a typical outdoor climate of 3 decades in Estonia. It contains only average data of outdoor temperature, relative humidity, wind speeds, and solar radiation. And if we compare summertime period, this high or test reference year to this measure period of 2014, see that only its outdoor temperature excess exceeds this 150 degree hours, and in case of dry, it's only 0.5. So a big difference in this year and the real year. In this, decisions need to be done using standard use profiles for lighting, power, appliances, occupancy, and this internal gains from these are presented this graph as a sum. So shell building is operable 24/7. So these standard profiles are for every room and need to be with standard profiles. Now opening as a difference between residential and non-residential buildings. So in case we need to look at design drawings, and there is information about whether or not the window is openable, and we have to then calculate the openable window airing area, and this needs to be included in the simulation, which algorithm, for example, if the zone temperature is high enough and out temperature is low enough, we can use window airing, and this window is opened in this case for 10% of the total area is used. And also from the design documentation, we get details for window panes with a specific claim, and also needs to be included into the simulation to make it accordingly. And results the analyzed 25 buildings, we saw that out of 25 or 68% did not comply with the regulation, and as you can see, some of these buildings are near this 150 degree hour limit mark, but some of them are heavily over this limit. So really, if this is not met, the building permit should not be given this building. Yes, this is a relatively new building code. We could see that this requirement was not fully established in practice. Only in 8 buildings the required calculations were included in the building permit documentation. And for findings, the methodology itself proved to be sound and robust. Some improvements were suggested, and in terms of critical room section guidance and so on. And the study was able to identify the parameters define these critical rooms as a combination of different measures by avoiding the risk of overheating. And for comments, temperature measurements showed that there is high risk of overheating in new apartment buildings. There were also many complaints from occupants, but we didn't have this data systematically. And 58% of the studied buildings comply with the requirements in Estonia. And we cannot directly compare the simulated and measured results because difference in weather data and occupancy behavior and so on. But we know that the high effect on overheating risk reduction had shading balconies. And we find this critical room that usually a combination of different factors such as southwest oriented windows, lack of external shading elements, and well-defined window-to-wall ratio values, and window-to-wall ratio multiplied with solar heat gain coefficients. And also a major factor was window airing area. So this concludes my presentation, and thank you.